hosted by the Center for Networked Intelligence at the ECE and RBCCPS IASC. Today's talk is by Dr. Nicolas Gast, and he will be speaking on mean field control for restless bandits and weakly coupled MDPs. Dr. Nicolas Gast is a tenured research scientist at Inria, Grenoble, France, since 2014, and currently visiting MIT for the semester. He graduated from École Normale Supérieure, Paris, France in 2007 and received a PhD from the University of Grenoble in 2010. He was a research fellow at EPFL from 2010 to 2014. His research focuses on the development and the use of stochastic models and optimization methods for the design of control algorithms in large-scale systems. Before we move on to the talk, we would like to request the online audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. Finally, we request the audience to please keep your microphones on silent for the duration of the talk, except while asking questions. And for questions, you may unmute yourself and ask Dr. Gast directly. Over to you, Dr. Gast.
Yeah, thank you for the nice introduction and for the invitation to this seminar series. Yes, so today I'm going to talk about, say, restless bandits and weakly coupled MDPs, and in particular how to use, techniques from mean field control to solve these problems. So this work is a joint work with two PhD students, Kimang and Chen, who recently graduated, and also that who were co-advised with Bruno Gojal, also from Inria. So before I start, let me say that do not hesitate to interrupt me at any time. Okay, if something is unclear during the talk, or if you want to learn more. So probably, I guess you're all familiar with the classical bandit problem, and what I'm going to talk is really kind of an extension of these things. So the classical bandit or multi-arm bandit problem is that you have a decision maker that is here represented as this giant beast with many arms. And so this decision maker at each decision epoch, is facing like n what we call arms, and at each decision epoch is decides to select one of these n arms. Okay, for instance, it might select this one, and this arm will generate some rewards. And so one of the really classical multi-arm bandit setting is the IID setting, in which at each time instance, if you select an arm, it gives a reward according to some probability distribution, and these rewards are IID, so they are always the same mean. But the thing is that the decision maker wants to identify the arm that gives the best mean, but doesn't know these means. What I'm going to talk about is a bit of a variation of this problem, which is the Markovian bandit problem, and here the name Markovian here. And why these arms are Markovian is because here I'm going to consider that each arm has a state. Okay, and as opposed to the classical setting where what you want is to identify the base because you don't know the rewards, here what I'm going to consider is that you really know, okay, the transition probability and the reward matrix of each arm. So here in all my talk, each arm will have a state, so the nth arm will have a state Sn, and you can send an action An to this arm, and it will transition to a new state according to some probability matrix, and it will generate a reward also according to the state in which this arm is and the action that you take. And your goal is to compute some optimal policy. So the policy is just a function that maps the possible states to actions. And what we'll see is that this policy will have some restriction, and this will what makes the problem hard to solve. And so you may say that here the first classical problem is a learning problem, whereas here the problem is not really about learning, but it's more about it's a computational aspect. Is how to compute this best policy. Still, these problems are really related, and in particular, that's just the example that I will to give you now. But in particular, they are related when you think of Bayesian models. Okay, and so let me just give two application example of these models. And the first one I want to talk about is what I call the applicant screening problem. So that imagine it's that you have a job, okay, that you want to offer to people, and you have n applicants for this job. And what I'm going to assume is that you have T rounds of interview, okay, and at each round you can interview a fraction of the candidates. So here, notation is not really important here, but it will appear later. But so alpha would be the fraction of candidates that I can interview at each time. And okay, for instance, I have 5 rounds of interview, and at the end of the 5 rounds, I want to select the best candidate. So I want to have to learn, the quality of the best candidates here. So now here, this is an example of a learning problem when you want to learn the quality of the candidates. But in fact, it's also an example of Markovian bandit problem. If you think of a Bayesian model, where here, for instance, each candidate will have an unknown quality Qn, okay? And what you imagine that Qn is something between 0 and 1, you can put some prior distribution on it. And when you interview a candidate, the result is some noisy estimate of Qn, for instance, a Bernoulli sample of Qn, okay? And at the end of the day, what you want is to identify the highest Qn. And here, when you take an action for a candidate, an action would be interview this candidate or not interviewing this candidate. This will give you different reward, different transition probability, depending on the success of the interview. A second example that I will also use is the job scheduling problem. And really, that's a problem that we face all the time in research, is to decide, what to work on. And the idea is that, okay, imagine that you, at the beginning of the day, you arrive at your desk, and now you decide, okay, what should I work on today? And there are different policies, to decide. One is, for instance, that maybe you have, you have a list of tasks. We all have tons of tasks to do. Some of them have deadlines, so maybe we want to prioritize the task with the earliest deadline, okay, which would be like the earliest deadline first policy. But also maybe some reward have a high risk. Some rewards gives a high reward. Some tasks gives a high reward. And so we need to decide. And so if we look at this model, they've been studied, for instance, in queuing theory a lot, and they are also, used for, a lot in data center today, where now the idea is that for this job scheduling, you would be a server, you have a number of projects or tasks that are in front of you, that are okay in your queue. If you want, you have a queue of all the projects. Projects might be coming because you have new tasks arriving, and your job is to decide, okay, who to serve first. So again, this research project is maybe the nice example that we can use. But for more practical application, you can also think of electrical vehicle charging problem. Where here you have a charging station, they have limited capacity, so you cannot charge everyone at the same time. And so these two problems, I will come back to, I hope I have time to come back to the two of them, but they are problems that have been shown to be computationally hard. What I mean by computationally hard is that, for some of them, they are shown to be like p-space complete, which is somehow harder than NP complete, or sometimes even X time complete, which means that you can't really serve them solve them. Sorry, exactly. But in fact, there exists some really nice heuristics to solve them, and that's what I want to talk today. And in particular, what I want to try to explain is that these heuristics can be somehow framed or can be thought of in terms of mean field control techniques. And so here, what is a mean field control? The idea is that what you have on the right is that you have a population of n arms. Okay, these arms might be my tasks, might be my the applicants, and so each time time is discrete. At each time, I want to send an action to this population of arm. Okay, and as I told you, I mean, this thing is difficult. And why is this difficult? Is just because this Markov process that you have on the right is a Markov process of dimension n. So if each arm has n states, okay, if n states for per arm, then it would mean that you have s to the power n states for the total mean population. So essentially, there is really an explosion of the number of states that you need to use for the system. But now, where is this idea of mean field? Is that now, I mean, mean field somehow, mean field approximation is like you make as if everything is every arm are independent, and then you try to solve this independent problem. And this somehow is, I mean, can be think of as a system where you have an infinite number of arms. Okay, and why is that? Just that because I mean, this is a thing that you find in to justify, for instance, mean field games. Is just to say that okay, if you have an infinite population of agents, each agent will have a limited impact on the other agents. Hence, you can't think of agents as being independent. And what is really nice is that if you think of these agents as being independent, I mean, many of the problems are much simpler to solve than the problem with n agent. And so you have sort of this weird things that as n grows, the problem becomes more and more, I mean, it becomes harder and harder to solve. But yet, at the same time, when n is equal to infinity, the problem is easy. And so the idea now is that, but if the problem for n infinity is easy, maybe we can just use this problem for the finite n solution. And hopefully, as n goes to infinity, our problem that is harder and harder will become, in fact, simpler and simpler because we can use this mean field control idea. And so this whole talk is sort of this is that how to use this mean field control for the finite n model. And also, second question is like how efficient is this in terms of what we're going to show is that for some problems we can use this n infinity problem to obtain asymptotically optimal policies. But the question would be like, how fast will this policy become asymptotically optimal as the population of n grows? Okay, so here is the outline of the talk. I will first present you what is the mean field control problem, what is this relaxation, and why this problem finite. Then I'll talk, essentially, I have two parts. The first parts, like 2 and 3, are about infinite horizon problem. And the last part is about finite horizon problem. And so for the first part, I will just, I want to go back to some classical notions of what is called index policies, in particular, Gitting's index and Whittle index. Just to maybe, to explain what is the definition and why it's related to our problem. And in particular, I will give you then some conditions under which they are asymptotically optimal, in particular at what rate. And also some nice result, I think, results that I found nice about how to compute these indices. And then last thing that if we have some time, I'll go over some results for finite horizon restless bandit that are solved using like both similar but at the same time pretty different techniques compared to infinite horizon problems. Yeah, so again, if you have questions, do not hesitate to interrupt me at any time. Otherwise, I will just move on. Okay. So what I mean, in this talk, the main model I'm going to focus on is that I have n arms that are statistically identical, meaning that they have the same transition matrix, they have the same they have the same state space, and one of the assumptions that I will use, mostly for simplicity, is that time is discrete and you have a finite state space per arm. And here I will denote just P and R for the probability transition and the reward for a given arm. And my goal here as a decision maker will be to maximize the expected reward. So here I wrote it for a finite time horizon, but let's say that this is the same. This could be the same. I mean, if you want to, you could put a limit as t equals to infinity when we think of the infinite time horizon. But the most important thing that I'm assuming is that here I'm considering like additive rewards, meaning that the total reward will just be the sum of the reward for all the agents. And so again, I have this population of agents. I want to choose one action per agent. And if I just say it like this, this is a simple problem because, if everything is additive here, then I have n independent problems. So the important thing here is that I will consider that I have a hard constraint, which is at all time instant, my actions need to satisfy some say inequality constraint. And so in particular here, what I'm mostly going to focus on is this Markovian bounded case, which is like the action that you can take for an arm is either 0 or 1. And 1 being I activate this arm, and 0 being I don't activate it. I'm going to just choose the passive action. And so here, the constraint here in that case, here you might imagine this constraint might be a vector, but here the C would be a scalar, which would just be at each time instant, I cannot activate more than C arms, okay, in total. And for instance, if C is equal to 1, you go back to this classical multi-arm bounded problem where at each time instant you activate one of these n arms exactly. And so the thing is that this constraint here is really what makes the problem computationally hard, because this thing couples all the small Markov processes. And so, in fact, in this talk again, I will talk about Markovian bandits. But in fact, what I will claim is that most of the results also apply to more general weakly coupled MDPs. And what are weakly coupled MDPs is just, essentially it corresponds to having a bit more general action. So you don't just have 2 actions per arm, but maybe you have more actions. And you have more constraint also like this. Okay, C maybe now is a vector. And so you have different actions that can have different costs that can consume different kind of resources. But again, most of the things that I'm going to talk about will somewhat translate into this weakly coupled MDP. But say not all, and I will come back to that at the end. And so just to simplify things, because I think it's easier and maybe more important, I will focus on this Markovian bandit thing. And just to comment on the term, but the idea of weakly coupled is just that here, my Markovian arms, these are like small Markov chains, so small MDPs, and they are mostly independent, but they are coupled only through the actions. And this is the term weakly coupled. I think where the term weakly coupled comes in is that they are coupled only through these actions. Okay, and now again, what we have here is that, okay, just because because I'm going to scale the problem when n grows. Here, what I'm going to say is that the number of arms for which I can take the action 1 is bounded by alpha n, okay, where n is some n is a scaling parameter, and alpha typically is a fraction. Okay, alpha is something between 0 and 1. And so the main thing that makes the problem hard, okay, is this constraint that at all time you cannot activate more than alpha n arms, and because it couples everything. Now, in fact, what we are going to do here is to relax this constraint by using the following constraint: is that at each time instance, okay, it is still for all t, I cannot activate more than alpha n arms in expectation. Okay, that's really the key thing, is that I have this expectation here. The expected number of arms that I can activate at each time is bounded by this alpha. And what I claim, in fact, is that this simplifies the problem a lot. Okay, in fact, it makes as if the arms were completely independent, and this can be solved by just a simple linear program. And I mean, here's just a one-page proof of why this is true, and this is just the linear program that we can write. And this linear program is just, it seems big, but as all linear programs, they are big, but they're in fact quite simple to understand. And the idea is that here, the most important variable is this YSA. And YSA is the probability that an arm is in state S and you take action A. Okay. This is my variable YSA, and the idea is that the reward now can be written just as sum over SA of RSA times YSA. Okay, this is the reward times the probability that I'm in this set action pair SA. And now, okay, what are the constraints? The constraints are, the first one is just like the Markov equation. Okay. The second one is just that I need to take one action. Okay, one action per state. Okay, and the last one is that the probability sum to 1. So these three first constraints are exactly the one that you would have if you consider some MDP and you write this MDP as a linear program, you would exactly obtain this first three constraint. And the only new thing that you have here is this relaxed budget constraint, and this is exactly the same the constraint that I wrote above here. And so this problem, you might, so you can write it as a linear program here, and it also can be written as what is called a constraint Markov decision process that are in fact all these kinds of linear programs. And this means what? This means just that the mean field control problem is easy to solve. Okay, so here I wrote it for the infinite horizon problem. In fact, if you want to look at the finite horizon problem, you can write the exact same problem, and you see essentially the only difference is that things depend on t, and so now the Markov equation, I have something like y of t here that becomes x of t plus 1. But apart from that, it's exactly the same problem, so I don't want to describe it really. Okay, so now how can what do I want to do with this problem? Now the idea is that, as I told you that before, I had some this problem. Okay, I should maybe here about this. Put an end here. I had this. Okay, well, let's forget that. I had this problem that if I have my constraints here, where I need to activate at most alpha exactly at all time, then this problem is computationally hard. Now what I did is that I relaxed my constraint here by looking at expectation, and now this is a linear program. It's easy to solve. And so because this constraint is a relaxation of this constraint, okay, the value of this problem here will be smaller than the value of this relaxed problem here. Now the question is, can we use the thing that we solve here to do something for the original problem? And so what's the difficulty is that how do I obtain this this V star rel, this value of this relaxed problem? Is that, what is the solution of my LP? The solution of the LP is just, a given x star, x, y star, it's somehow a given deterministic trajectory. And in fact, what is difficult is that in general, when you look at so xn will be here the state of my stochastic model. And in general, we see that we cannot really use, so x here is the state and y is the control. And we cannot really use the deterministic control because in general, the state is not the same. The stochastic state will not be the same as the deterministic state. And so this is what we're going to study next, is how to use this this problem with this infinite problem to build a policy that is asymptotically optimal as n goes to infinity. And so, just to give you an idea of where this, where this fits in the literature, I will in fact, again, I said, study two problems. The first one is the infinite horizon problem, where what we're going to study is things called like index policies. So index policies were introduced in the 60s by Gittings. Then they were generalized into what is now called Whittle index I think I wrote 98, but it's probably 89 in fact. And then they've been studied a lot by, many authors, since then, including, for instance, Nicolas, who produced a lot of papers on that. And so, what is shown essentially for this, what has been shown here in the past, that Whittle index are asymptotically optimal in some sort of conditions by Weber and Weiss. And what the new results, I will talk about this result, and the new results I want to talk about today is that the rate at which they become optimal. First is that exponentially fast. And the second thing is how to compute this index in a maybe more efficient manner than what was known. And so the second line of work that I will be briefly talking about is the finite horizon problem, in which there is something like similar to index policies that has been introduced and that are called, for instance, LP index in some papers. And you'll see that there are a bit different results, because here index policies are, say, almost always asymptotically optimal, whereas here, this kind of index policies or product rule, if you want, I mean, they are not really optimal, but say that the result is that when they are, they become optimal exponentially fast. And so this second line of work is more recent. I think it's, I mean, you have find some recent paper by Brown and Smith and Frazier and different co-authors in 2020 or more recent papers. Okay. Okay, so now let's try to, so I want to talk about index policies. And I mean, first of all, what is an index and how you want to, how you can characterize them. Okay, so the idea is just that if I look at my mean field control problem, I have what is called a constrained MDP. And what is the constraint here is that, okay, I have priority, transition, rewards, and I want to find a policy such that in steady state, somehow the expected time that I take the action AN is equal to alpha. Okay. So I want to maximize the reward, given that in steady state, the expected time that I take action AN is equal to alpha. And so how do you solve such a thing? One thing, I mean, you can use linear programming, as I said, but in fact, here you have a constraint. One thing that you can use is also some kind of Lagrangian relaxation, which is the idea is that what you're going to do here is that you will apply a penalty for activation. So again, here, recall that AN is between 0 and 1, okay, and that 1 is my active action. And so here, when I talk about this penalty, I just mean that if you take action AN is equal to 0, you have no penalty, but if you take action AN equal to 1, you have a penalty of 1. And so the idea is that for proper lambda, the problem that is here and the problem that is here are equivalent. Okay, there exists a lambda in general, I mean, under like strong duality, but here everything is linear, so there should be no problem. And there exists a lambda so that these two problems are equivalent. And somewhat, the index use some kind of this idea. Okay, more precisely, what we're going to look at is you vary lambda, and you think of what is the optimal policy as a function of lambda. And so here, that's what I try to represent for some imaginary problems that on the x-axis, I have a penalty lambda. And the idea is that lambda is a penalty for activating, which means that when lambda is equal to minus infinity, here the policy should be like I activate all in all state. Okay. Now, and so that's what represents here on my graph. Somehow like the blue here, I imagine that I have 4 states, and the blue things mean that I activate, and the white mean that I should not activate. And so here, for a given lambda, okay, for instance, lambda might be here. For a given lambda, the policy would be I activate when I'm in state S1, S3, and S4, and I don't activate in state S2. So yeah, the policy here would be like, for instance, here the pi of S1 is equal, and policy in state S1, S3, and S4 is equal to 1. And the policy in state S2 is equal to 0. And now, okay, at the same time, okay, if when lambda is minus infinity, I should not, I mean, I should activate everyone. If lambda is plus infinity, I should activate no one, okay? Because here, I mean, penalty of activation is minus infinity. And what looks reasonable is that, in general, for all the states, it's optimal to activate them. I mean, for low lambdas until some value, and then after that, it's optimal not to activate them. Okay. And so, if this is the case, what we obtain is that what we call we call lambda 2, for instance, for state 2 will be the value at which it becomes optimal. I mean, at which the action jumps from activating to not activating. Okay. Here, lambda 2, and for instance, here would be for state 4, for state 1, and for state 3. And now, the idea is that if we define the index, I mean, this is a way to define this index. And Whittle index policy here is just that this index will give me a way to choose which one to prioritize. And would be, for instance, if I have two arms in front of me, one is in state 3 and one is in state 4, then I should activate first the arm that is in state 3, and then the arm. If I have two arms like state 3 and 4, and I need to activate only one of them, I should activate the arm that is in state 3. Okay, and if I have 3 arms in state, say 1, 2, 4, then I should only activate the arm that is state 1 if I need to activate only one. So now just I say that this is the definition of index policies. In fact, this is the definition if there exists such a lambda s for all states. Okay. Now, what should be clear is that, or maybe it's not intuitive, but this is not always true. Okay, meaning that there are some models for which it is not. I mean, there is not a lambda s per state. Okay, and in fact, there are some models for which okay, there are some models, for instance, for which for state 2, for instance, it is not optimal to activate it here, not activate here, but it's optimal to activate in the middle. Okay, and these models are called non-indexable. I realize that I'm maybe slightly running out of time. So yeah, just to maybe give an illustration of what are these index policies, maybe to make something more concrete. Now, with coming back to this job scheduling example. So now imagine that you have two jobs. Okay, one job is of size 10, the job X, and the other job for the job Y, the red job, you know that it's going to be either of size 2, probability 1/2, or of size 18, probability 1/2. And the question is that which one of these two jobs should you run first if you want to minimize the expected completion time? And so what sort of maybe it should be a bit intuitive here is that here the job X, you know that it's going to take like 10 hours to complete. But for the job Y, maybe there is a high chance that I will complete it really soon. And so the intuition would be, okay, let's start to run the job Y for 2 hours, okay? And let's see if we finish the job or not. And if this job is not finished, then we'll move to job X, and then we'll resume later. And so you can really frame it in terms of index policies here by considering this penalty model. And what is the penalty here is that here what we consider is that running a job costs, say, €1 per second, and you can stop the job at any time. But say that if you finish the job, you earn some amount of money that I denote X, okay? And here the index of the job would be the smallest value of X so that you are willing to start running the job, okay? And what this means here is that for the job X, you know that I need to give you 10, okay, if you want to start running the job. Now, the thing is a bit different for the job Y is that if I give you 4, okay, you say, okay, you give me 4, then okay, there is say there is half a chance that I finish this job, and in that case, I will give 2. And otherwise, what I can do is that I can just run it for 2 hours and I'll stop. Okay, and so here the idea is that at the beginning of the execution, here the index would be 10, and here the index would be 4. And so the index policy would tell you to execute first X and then Y. And in fact, okay, I have a more maybe complex example in the slide, but the idea is that then what you can do is that you can really compute the index as a function of the age of the job and use it to schedule any kind of job here. Okay, I don't know if are there any questions so far?
Oh, it's good, Nicolas. Please continue.
Okay. So now, so the thing is that what I thought is that this index is a way to solve this n equal infinity problem. Now, what we have is that in fact, Whittle index policy is just it's a priority policy for the finite model. And so there's been some work to understand, like, what is under which condition these things become optimal. So of course, if you want Whittle index to be optimal, then you need to assume that the model is indexable, otherwise your policy is not well defined. And in that case, what you can do is that, okay, you take this index policy, this is a priority policy, and it's not really hard to show that that this process X at the limit, so here XS of t would be the fraction of arms that are in state S, okay? And it's not really hard to show that the policy, the Whittle index policy, gives you some piecewise linear deterministic dynamical system for the infinite model, okay, that is of that form. And in fact, it can be shown, that's essentially what was shown by Weber and Weiss in the 90s, is that if this dynamical system has a unique attractor, then Whittle index policy becomes asymptotically optimal. And what we added recently
sorry,
was
Nicolas,
that
this you're assuming the limit of your n particle system, right? This xt, what you're calling.
Yeah. So here the idea is that okay, I have x s n, for instance, t would be the fraction of arms in state S for my finite n problem. And the idea is just that if you let n goes to infinity, this becomes deterministic. Okay, but more. I mean, in fact, here, how to say? I mean, the equation that I write here is, I mean, it really comes back from the solution of this LP system essentially. And so what you can do is that this deterministic problem, I mean, this is the deterministic problem, and if this problem has a unique fixed point, a unique attractor, sorry, then with an index policy that's asymptotically optimal. And in fact, what we can show is that if this is the case, then the suboptimality gap with an index policy is exponentially small. And so maybe also to understand a bit, to give you a bit more understand a bit more the questions that now again, like what we have is that xn of t would be the fraction of arms that are in state at time t. And what you can show essentially is that xn of t plus 1 is equal to a deterministic, deterministic value, deterministic as a function of the xn of t, plus some noise, okay? That is because, if you have n arms and given the action, all the arms behave independently. And so what you have is that this noise, as the number of arms goes to infinity, decreases to 0, okay? And so the xn of t plus 1 is equal to my deterministic value plus some 1 over square root n stochastic noise. And now what you can show is that essentially, if this model has if this dynamical system has unique attractor, then the steady state distribution of this guy with of the process with n will concentrate on this unique attractor. Okay, and this is like standard, say, large deviation theory. And now what you can add on top of that, that if this attractor, I say that this thing is piecewise linear, and if the attractor lies within strictly within a piecewise linear region, then you can use some linearity of expectation to show this exponential convergence rate of the Whittle index policy. So this is like my one page proof of the previous result. And yeah, just to conclude on Whittle index, that so to us this first result was interesting because what is shown in reality is that when you apply Whittle index for many problems, it is really close to the optimal policies. The value of Whittle index policy is really close to the value of the optimal one, and so here somehow it gives a sort of intuition that yeah, it is true because of this linearity effect of the expectation that really makes the thing exponentially close to the optimal. Now, see, when you want to apply this index policy, there is a question of how to compute Whittle indices. And so for that, we went back to this classical definition of index policy that the index of a state I here is the penalty such that somehow you choose to activate or not when the penalty is lambda I. And so, I won't go back into the details, but details are in the paper, but somehow the definition to us was not really precise enough, okay, to really characterize what is optimal, what means indexability. But now, in fact, we came in with sort of, more natural definition of optimality that is non-ambiguous. And that is that we want to compute the policies that are called, that we call our Bellman optimal. And so what is a policy that is Bellman optimal? A policy that is Bellman optimal if it satisfies Bellman equations for average reward. And the idea is that, so these are just the modified Bellman equation for infinite reward. And so similar to the discounted version, here we can also define some Q value. Okay, QIA would be the Q value of a state action pair IA, and that depends now on lambda. And this gives us something that is called the the active advantage, which is just the Q value of the action 1 minus the Q value of the action 0. And again, this is dependent on lambda, where lambda is my penalty. Another good thing with this, I said, unambiguous definition is that now, in fact, what is really easy to show is that you can show that an arm is indexable if and only if this active advantage crosses the x-axis only once, okay, or at most once. And so, why is this useful? Is that what you can show, in fact, is that this Q value or this B value here, this B value satisfies some, for a given policy, satisfies some, it satisfies a linear equation. And so you can, you can use it to obtain some efficient algorithm. And where, the idea is that if you fix the policy pi, you can compute easily this function. And so this function is piecewise linear, and the only places where where two pieces are connected is when you are at this value, okay. And so what you can do essentially here is that you'll start with the computing. At first, the policy is a policy that activates everyone because you know that it's optimal. And then you look at the first state that intersect 0. And now you know that you need to change the policy. And if you need to change the policy, what you need to do is to modify some of the slope of this curve. You know this piece was in there, but now you need to compute the new slopes of these curves. And now, essentially, to compute the new slope, there is something called the Sherman-Morrison formula, which is, I think, quite an interesting formula. It's just that here you need to invert one matrix, okay? And the thing is that if you change the policy for only one state, only one line of this matrix will change, which means that you can compute the new inverse in a reasonably, in a small number of computations. And so by doing so, you can compute these new states pretty easily. And now, the last thing is that here, because all of these things are sort of matrix multiplication, you can use something like Strasson's optimization and our divide and conquer algorithm to obtain something that is faster and that computes your index at a subcubic time. A bit like you can multiply matrices with a subcubic complexity. You can also compute this index with a subcubic complexity. And so this, for instance, just to conclude on this graph, here what I showed is that we use this ID to do a small library that computes Whittle index, and at the end, what is shown here is that even if you have problems like matrices with more than 10,000 states, which would be like, so this is here, the size n is number of states for now. So it means that the matrix of size 10,000 by 10,000. So like this is 100 million of numbers, okay, in my matrix. Even for such a big model, you can, compute the index of this model is in like, a minute or a few minutes. So it is relatively fast. Okay, do I have still a few minutes or should I stop there for questions? I don't know.
I would say you can continue, Nicholas. We'll take questions.
Okay.
Thanks.
Okay. I mean, anyway, so now I want just to give you small ideas of about what occurs in the finite horizon problems. And anyway, it's going to be pretty quick. But now the idea is just that for the infinite horizon problem, what we have is that we have a way to define indices, and these indices give us some priority policy. And this priority policy is a policy that does not depend, I mean, these priorities do not depend on time, okay, they are fixed forever. And essentially, under some mild conditions, these things are asymptotically optimal as n goes to infinity. Now, there's a bit of a difference when we go to finite horizon problems, is that when we have finite horizon problems, what is the output of the LP problem is solutions like x star, y star that depend on time. Okay, because I mean, of course, finite horizon problem, the policy has to depend on where you are, on what t is. Okay, whether you are close to the horizon or far. And here, this is just a representation, this graph of what is the x star and the y star. So here, x star would be like, for instance, I have two states here, and this is like y star S1, okay, y star S1 also. And so here the blue thing means that I'm taking action 1, okay. So this is like, this corresponds to action 1. And the white thing corresponds to action 0, okay. So it means that here I reordered my state for a given time so that here S minus contains all the states that I'm not activating at all. S plus contains the state that I'm activating completely. And in the middle, I have the states that for which I take both action 1 and action 2. And so now the thing is that this was for the deterministic territory x star. Now, if I go and I have my stochastic system, I know that now I'm not going to be exactly in x star, but I'm going to be in xn, okay, which probably is different. You see that these boxes are, for instance, smaller, and this one are in fact a bit bigger than the one above. And so now the idea is that how can you translate the decision that you take, that the LP wants to take, into the decision that you need to take now here. And the idea is pretty simple. It's just that, in fact, if you have a single state in S0, you can just apply some priority rule. And the priority rule would be just, okay, you first fill the state in S plus, then you need you fill the state in S0, and then, for instance, maybe you have to complete with state in S minus, and I mean, just to fill this alpha constraint. And the idea is just that if you do this thing, it's easy to show that the policy that you obtain when you apply it to this thing will exactly give you x star, okay, and has some really nice properties, like it's locally linear, it's Lipschitz continuous, it's piecewise linear, any kind of thing. Which essentially means that if you use this policy, then you can rewrite the result that I wrote before for the exponential convergence rate of Whittle index policy into this finite horizon problem. And the proof arguments are the same, meaning that you have concentration argument and linearity of expectation before. The only difference, I say, or the main difference between the two, is that for Whittle index policy, the models that satisfy this condition are, I mean, almost all models satisfy the condition that imply that the exponential convergence rate is true. And in fact, for finite horizon model, you have lots of models that do not satisfy this condition, which means that in general, the convergence rate that you obtain is really less good. And maybe just to conclude, just to come back to this applicant screening problem that I talked about at the beginning, and that is in fact taken from the Brown and Smith paper, is just to this is a problem when you have applicants, and the way you frame it as a Markovian bandit problem is to use this Bayesian framework. And for instance, you can put some prior over the quality, like a beta distribution, a 1-1, and essentially the 1-1 will become your state of a candidate. And so now, for instance, if you interview a candidate, it's in say 1-1, and depending if the candidate gives you a good answer or bad answer, and here it's essentially with priority 1/2, you move the candidate to state 2-1 or 1-2. And now again, if it gives you a good answer the next time you interview it, or a bad answer, it gives you some the state evolves like this. So it's a classical like Bayesian bandit problem. And the idea of this finite horizon budget problem is that, in fact, it's relatively easy to find example, for instance, with this thing, where the model do not satisfy this thing that priority rules are asymptotically optimal. And I think that this is an example taken from their paper that shows that. I will not give you details here, but the important thing is that because of that, the rate at which these problems are asymptotically optimal, in the case where there is no exponential rate, is slower and is just at rate square root n. Okay, just to conclude. So today I talked about Markovian bandit. And in particular, this idea that for this problem, you have a mean field control version of it that can be solved by some linear program. And it's nice because then you can apply it back to the original problem. And in particular, the main thing I focused on here today was to show that in many cases, you have simple policies like priority rules that are optimal. So they are not always optimal, but when they are, essentially, almost always when they are asymptotically optimal at exponential rate. Okay, and moreover, you can somehow compute them sometimes pretty easily by using some ideas from index policies, which essentially corresponds to find the right activation price for the problem. And this is proven to be very efficient for many practical systems. Okay, so in this talk, I mostly talk about finite state space, where I know all the parameters. Of course, when you go to like learning these problems or continuous state spaces, things becomes more complicated. But I think for now, I would like to stop to that. Thank you.
Thank you, Dr. Gast, for an informative talk. We can take a few questions.
So one quick question, Nicolas. So this the recipe which you told us, right, how to use this Whittle index by taking this Lagrangian, multiplying it and checking whether this is acceptable or not, these actions. So I understood a little bit, but do you have a tutorial or a paper which if you read this and you'll be able to follow all the details which you did not present here?
Just to answer on the definition of this index, or on
the way you present. If you go back like a couple of slides, right? I mean, you had this. So that one, so just go back.
No,
right?
Again,
so these things, So like this, after that actually. So like this age based, right? You said like based on this you select. So, like,
yeah. So I guess you mean, so yeah, how to define, how to compute these things, like these kind of things.
Right. So you give this whole recipe, right? You do this and you do that and you do that, right? So, I mean, I'm sure you have written papers, but is it like just a general recipe, like a tutorial, which we can just follow, or?
I guess that, yeah, I think that the main reference that I have on that is the paper that is here,
This one.
computing
Okay.
Whittle and getting index in queuing time.
Okay.
And I'd say that, yeah, I'd say that it's probably, I mean, it contains all the details. Maybe, yeah, maybe some parts are technical, but I think it's yeah, it should be easy enough to to follow.
Sure, thanks. Well, so one more question I had was, when you were presenting this, the first, the example which you're like discussing in the end, the interview problem. If you go back to like that example one, I didn't quite understand the setting and the constraint of the question itself. So if you don't mind just explaining super quick.
Yeah, sure. So now the idea is that, let me use this picture as base. Sure. Now the idea is that here you consider that you have n candidates in front of you at the beginning,
right?
And at each time, so you have here you have 5 rounds of interview. Okay, 1, 2, 3, 4, 5. Okay, this is time. And at each time, what you do is that you can interview 25% of the candidates. So first,
this is a constraint given to you because like switching this percentage would probably give you different performance, right? I mean, if
sure. No, this is really like that you imagine that you have this is like your interview budget. Okay. But I don't say that 25% is the.
But with this 25% is a bit. I don't understand this, because initially, if you're doing so, this 25% and the number of applicants, is it variable or is it fixed in every stage?
No, these are the same applicants. So okay, maybe to make things more concrete, imagine that you have I don't know, 20 applicants for your position. You want to take 5 of them, okay, and you do interview one by one, and the only thing is that at each time you can interview at most 5 people,
okay, because
this is the resource that you have, okay,
right.
And so the idea is that then at the beginning you have all the candidates, so you interview anyone, you don't care, you don't know the people, they're all the same here, and so you will interview all the 20 candidates, and not all, but you will interview 5 candidates, okay, and some of them will give you good answers, some of them will give you bad answers, and these are these 2, and the other one you did not interview them yet, so you don't know, who they are. And then at the second round, you will choose again over 5 candidates to interview, and you may either choose from the same candidates that gave good answers, or you may choose from the other candidates that you did not interview so far.
So it's a sampling question, that how do you put probability on who to choose for interview next round and so on and so forth, right? Okay.
Yeah. And so the idea of this, for instance, this graph is that it shows you the optimal policy, which is at the beginning, of course, you interview people from this group. And now at the next round, you also will interview people that you did not interview so far. And so they will go here. And then at the next round, what you see that now, in fact, the people that gave you 1 bad questions, you just discard them, okay? Because you don't have enough interviews, so you just discard them. And then what you see here, that you will need to interview some people from this group and some people from that group. Okay, and then again, you interview some people from this group, some people from that group. And at the end, what you do is that all people who gave you like 2 good answers, you will admit. And all people who gave you 1 answer, you will admit, and the other one, you will just reject them.
And you round continue until you have seen everyone, I'm guessing.
In fact, you don't even see everyone here. You see the the blue, this light blue is the
Right.
people you did not interview yet. Okay.
Okay.
And these people you didn't interview because it's just that if you have 5 rounds of interview and you want to select 25% of candidates at the end, and you can only interview 25% of candidates at each time.
Got it.
You don't have the time to interview everyone.
So and then what are the some optimality guarantees here? Because you did not see anyone. So what guarantees do you get here in such a scenario? Like if we do this, I mean, yeah, you'll definitely get somebody who's good, but maybe there's somebody better, right? So
sure. No, what you get here is that now if you assume that the candidates have a beta prior or 1-1, then what you get at the end is that the expected quality of candidate is like 0.733.
Okay.
So you essentially get almost the expected quality of candidates is 75 almost.
Okay, understood.
Which is better than the average candidate, which is only 0.5.
Right. Got it. Thanks.
So, but it's true that here this is an example where the information, the feedback that you have is really small at each time step because it's only a 0.1, feedback.
I don't have any more questions. Thank you. Thank you very much, Nicolas.
Yeah. Thanks for the question. Yeah, good question. Thanks.
Hi, Nicolas. I have a question. So you said that one of the optimality conditions is, one of the conditions for these convergence problems is that the problem is unichain for all possible policies, right? But what if I know it's unichain for specific policies, but not unichain for, there is some terrible policy under which it's not unichain, but I don't know a priori if it's unichain in that terrible policy. Or rather, I don't know if that terrible policy is truly terrible in that case. Do these results still hold in those cases?
Just I'm not sure. Did I talk about unit chain?
I think that the idea of a global attractor under all policies is part of this, right?
Mm-hmm.
Or does it have to have a global attractor only under the Whittle index policy?
Yeah, no. So here, what I'm assuming here for Whittle index is that I'm assuming that only the Whittle index policy has this unique attractor.
Okay.
And also, what is a bit special here is that what I'm saying is that I'm assuming that Whittle index policy has a unique attractor. But here this is for the deterministic approximation of the system. And so, for instance, I'm not really assuming that the underlying Markov chain has an attractor. I'm not really assuming that the Markov chain should be unit chain or whatever. Probably it is implied by this, but it's this is a condition. At least this condition is really that for the deterministic dynamical system that I wrote here, and again that is an approximation of the version with stochastic noise.
Right. But wouldn't it be possible if your Markov chain can go to doesn't have like a stationary distribution, then the dynamical system that corresponds to the mean field limit might have this sort of a simple case, like it goes from 0 to 1 to 2, then back to 0, sort of in a revolving fashion. Then if you start with everyone at 0, then it just sort of keeps rotating around and around.
Sure.
Yeah. So, and
no, you're perfectly right that in fact it's so one of the things that there are two different answers, but the first thing that in this result, I write it on the slide with discrete time model.
Yeah.
But in fact, you can, I mean, in the paper you'll find the same result for continuous time problem.
Right. Yeah.
So in that case, where, for instance, one of the things that distinguishes discrete time and continuous time Markov chain is that is aperiodicity. You know, continuous time Markov chains are always aperiodic, whereas discrete time Markov chains are not. And so, what is true that for discrete time Markov chains, it's pretty easy to construct Markovian bandit problems where all the arms have nice properties, but because there is some, I mean, because of your constraint, the overall model has some periodic behavior, and it might have lots of strange behavior. So it might not be unit chain, even if all the arms are unit chain, then maybe the overall model is not is multi-chain because of this somehow periodicity issue and synchronization between the action of different agents. But now what is true also is that even if you look at continuous time model, so you get rid of all these problems of periodicity, but now it is still possible that that the assumption that I wrote here, that pi whip as a unique attractor, is not true. And in fact, if you look at the paper by Weber and Weiss, they give an example of a simple bandit problem in which, in fact, if you want, you have an attractor, of your system. No, you have a fixed point of your system. But in fact, what is an attractor is some is a cycle. Okay, you have a limiting cycle, and in that case, what is clear is that in that case, Whittle index policy is not asymptotically optimal for the models that have cycles.
Right. Okay.
And somehow it is the thing that you having a unique attractor somehow probably guarantees that the Markov chain is unit chain. So I mean,
right, and you only need the unique attractor to exist for the Whittle index policy for this whole thing to work. You don't need to worry about some other arbitrary policy where things can go horrible. Right. Okay.
Yeah, exactly. You only need it for Whittle index policy.
Okay. Thank you.
Yeah, welcome. Thank you.
Thank you again, Dr. Gast. The link to the slides will be posted on the web page. Thank you, everyone, and have a great evening.
Thank you. Bye, everyone.
Bye.
Bye.